the primary tool that we're going to use here is something called a matrix. So we'll start with a definition. So a matrix is a rectangular array, and in this class primarily would be numbers, but it could be other, these matrices could contain other kinds of mathematical objects like a variable or things that you haven't talked about in this course per se. But so what does a matrix then look like on our sheet of paper? So we'd use like these square brackets. And then a matrix would just have like some numbers inside of it. So when I look at this matrix, how many rows do we see in this matrix? We see 2 rows, right? And then how many columns do we see? 3 columns. Everybody kind of see that? So again, remember that rows go left to right and columns go up and down. So we can use that this matrix has 2 rows and 3 columns to describe the location of some of these numbers inside of our matrix. So for example, if I'm interested in this number -5, we might want to describe where in the matrix this -5 occurs. So typically, we're going to give a matrix a name. So usually we use the capital letters to name our matrix. So I'm going to call this matrix A. So the numbers that are inside of this matrix, I'm going to name with lowercase letter a. And then I'm going to describe the specific number inside of that matrix with a subscript. So the subscript I would do for the -5 is 1, 2. That's a 1 and a 2. Because that -5 is in the first row and the second column. And worth stating here, we always write the row first and the column second. Okay. And that should be easy to remember. When we describe a point, what order do we write the coordinates for a point? We write the x first and the y second. What direction does the x coordinate describe? Left and right. What direction does the y coordinate describe? Up and down. When we describe these matrices, we describe row first, column second. Rows go left and right. Columns go up and down, just like the x's and y's do, right? So it should be easy to kind of remember that. Just remember it's just like a point. So if I asked you which number is A23, what is that one going to be? That's going to be the second row, and the third column, that would be the 2. What if I asked you what a 3, 3 is? So that doesn't make sense, right, that question? So you don't write 0. You would say something like, this doesn't make sense. Why doesn't this make sense? Yeah, there's not 3 rows, right? So you can't even talk about something like this for this matrix. Okay, so we've described a little bit about like how we're going to talk about the parts that are inside of our matrix. Right? We're going to describe their locations by saying what row they're in and what column they're in. What we want to do now is we want to talk about ways to describe a matrix in general. So one way that we can do that is by talking about its dimension. So when we want to talk about the dimension of a matrix, we're just going to talk about it the same way we would describe like the dimension of a room. So if your room is like 12 feet by 15 feet, right? If it's 12 feet long and 15 feet wide, we might use a description similar like that to describe the dimension of a room. We'll use a similar description to describe the shape of our matrix. So we'll describe it as the number of rows by the number of columns. So let's say we have this matrix B. And I ask for the dimension of matrix B. So the DIM there is the notation we'll use for the dimension. And we'll just put a parenthesis around the matrix that we're finding the dimension of, just like it's an operation or something. So how many rows does matrix B have? 3. Rows go left and right. 1, 2, 3. And the number of columns is 2. So this matrix is a 3 by 2. To kind of extend this definition, we have a special term that we use in a certain case. So if the number of rows is equal to the number of columns, we call that a square matrix. And square matrices are going to be important a bit later on, probably not today, but next week. Sorry. There, we call that. So let's say we have this matrix C. The dimension of matrix C is 2 by 2. So what can we say about matrix C? It's a square matrix. The number of rows and the number of columns are the same. Okay? Everybody feel reasonably comfortable about kind of what a matrix is? so far. Okay, we haven't done anything too tricky yet, just a bunch of definitions. But the definitions are important because when we get to the complicated stuff, they're all kind of built out from these definitions. So we should go slowly through this and make sure that we're understand what it is we're talking about. But nothing here has been too tricky. What we'll start doing now is defining some operations, like how we can combine these matrices together. That's ADD, the word add. Okay, so we can add two matrices together by adding their corresponding entries. So that's like our word definition of matrix addition. Let's write out kind of symbolically what that would look like. So we have a matrix A and a matrix B, and I've just written a 2 by 2 matrix, but this extends to really matrices of any dimension. If I add these together, I'm just going to add the first entries together, and then the second entries will get added together, and then the third entries would be added together, and the last entries would be added together. Everybody feel okay with that idea? Let's do a numeric example just to make sure we kind of got it. What would the difference be if this was subtraction, though? Just minus signs instead of plus signs, right? Everything works exactly the same. So let's say we want to add these two matrices together. So my definition says that I can just do 2 plus 0 to get the first entry, -3 plus -1 to get the second entry, 4 plus 6 to get the third entry, and then 1 plus 10 to get the last entry. So I'd have 2, -4, 10, 11 as my final answer. So this is also pretty easy, right? This works exactly like we'd hope it to work, right? You just basically add the corresponding parts together and that's it. Everybody okay with that idea? Let's do one other example here. What if I wanted to add these two matrices together? Does this make sense? So what are we going to add these things with? Why? There's no zeros in the first matrix. This we cannot do. We'd say that this is undefined. So what is the dimension for this first matrix? That's 2 by 2. And what's the dimension for that second matrix? What is it? 2 by 3. So our conclusion is here. Is that matrix addition or subtraction is only defined when the dimension of matrix A is equal to the dimension of matrix B. If I don't have corresponding elements to add together, I can't do the addition. So that's an important thing to kind of keep in mind, right? So we can't add any two matrices together. That doesn't work. They must be the same dimension in order to be able to proceed with the addition or subtraction. Okay? Okay. So the next things we want to talk about is, now we can add and subtract matrices, right? We should be comfortable doing that. Now there's actually two types of multiplication we can use with matrices. Today we're going to only talk about scalar multiplication. We'll talk about matrix multiplication probably next week. So if we want to talk about scalar multiplication, the first thing I want to do is define what I mean by a scalar. So when we talk about a scalar, what we really just mean is it's a real number, like 7 or a half or negative 1.6, just a number, okay? Not a matrix is the key there. So when we talk about scalar multiplication, this is the product of, shockingly, a matrix and a scalar. To do that multiplication, we multiply the scalar to each entry in the matrix. So just like we did for addition, we've written a kind of in words definition. But let's also write a symbolic one, because oftentimes the symbolic definition is going to be kind of more useful to us going forward. So if I have k being a real number, and A is some matrix, and just for the sake of example, I'm going to say A is the 2 by 2 matrix described here. So if I do k times A, that's the same thing as k times the A11, A12, A21, A22. And the definition says we just need to multiply that scalar to each entry. So I'll do k times A11, k times A12, k times A21, and k times A22. So we have a verbal definition. We have a symbolic definition. Probably time to do some numeric examples so you can really kind of get the feel for how we're doing this. So let's say I want to do 2 times the matrix, -3, 1, 5, 6. So my definition for scalar multiplication says I'm going to take that scalar and I'm going to multiply it to each entry in my matrix, which is going to give me this result. So again, hopefully this feels pretty easy, right? Just multiplying some numbers together, and it's like, okay, that's easy enough. I just multiply to everything. You know, no big deal. So these first 3 matrix operations, if you want to count addition and subtraction separately, are pretty easy, right? The next ones that we'll talk about next week are a bit more difficult to do by hand, but not so bad. But before we start talking about those, I want to talk about some properties for these 3 operations. So for addition, subtraction, and scalar multiplication. So the first question that we're going to investigate is the question, is matrix addition commutative? What do we mean when we say commutative in a mathematics setting? It basically means, is A plus B the same thing as B plus A? Now we know this is true for real numbers, right? 2 plus 3 is the same as 3 plus 2. But it may not be the same thing for matrices. Let's think about it for a minute. What do we think? Do we think that this is true? Yes. Okay. So it is true. Those of you that kind of thought about it for a minute said, yeah, I think that has to work. How would we go about trying to prove this? Well, what we'll do is we'll take the left-hand side. That's A plus B. So if I do this for a 2 by 2 case, matrix A can look like that, and matrix B can look like this. Yeah. I just want you to see what it would look like and how this differs from like a geometry kind of proof, because they are kind of fundamentally different in what we're doing. So I can write A plus B as this matrix here on the right. Right? Everybody's okay with that? Basically, we just applied the definition of matrix addition. Now if I take the right-hand side, that is B plus A, I can do the same thing, right? Everybody okay with that? So basically where we're at is to show that A plus B is equal to B plus A. We need to show that this matrix from the left-hand side is equal to this matrix from the right-hand side. Oops. So that's what we would need to show in order to kind of prove this. So what does it mean for two matrices to be equal? Let's treat this as an aside, because this is not necessarily part of the proof, but it's like we need to understand what this means in order to kind of do what we've said we needed to do there. So what do we think that means? So for two matrices to be equal, two things have to be true. What do you guys think that those two things are? If you were just to tell me, like, if I asked you what does it mean for two matrices to be equal, what would your instinct kind of tell you would have to be, what would have some characteristics that they would have to have? They have to have the same dimension, exactly, so that's one part. Okay. And then what do you think the other piece would be? They'd have to have the same numbers in the same places, right? So the way I'm going to write this is that each entry in matrix A must equal the corresponding entry from matrix B. Everybody's okay with that idea? So let's look above. So it should be clear that the dimension of A plus B is definitely going to equal the dimension of B plus A, right? If we just look at what we have here, this guy was A plus B and this guy was B plus A. They definitely have the same dimension, right? We have that part. So, for A plus B to equal B plus A, this is true if the corresponding elements are equal. So, for example, I'd have to say A11 plus B11 is equal to B11 plus A11, and so on and so forth for each of those entries. Now, what kind of mathematical object are these little a's and little b's here? I'm sorry, what? R? What are these little a's and little b's representing? What kind of objects are they? Shapes? So these little a's and little b's are just real numbers, right? They're like a 5 or 6 or -2 or 0 or 1.8 or 5/3 or they're just numbers, right? And are the real numbers commutative? Yes. And so we're done, right? So what was the key here is that adding two matrices comes down to adding each entry, and because the entries are real numbers, and those commute, the matrix addition commutes, right? And this is a really kind of familiar proof tactic where you take one structure and use its definition to think about it in terms of another structure. In geometry, you guys frequently did this, where you proved that two things were congruent by converting them into equations using properties of equality and then translating them back into congruences, right? Which is basically what we did here. We took this matrix addition and translated it into just real number addition and then said, oh, look, those two things are equal with real number addition, and then we could translate it back to matrix addition, just like you did in geometry class. So even though there wasn't two columns here, it was more of a narrative explanation, it still kind of used that same technique. Okay. The next thing I want to ask is, what is the additive identity for matrix addition? When I say additive identity, what do I mean? I want to know what I can add to matrix A so that I just get matrix A again. Okay, so that's what we mean by like an additive identity, is that it maintains the identity of whatever you're adding to it. It doesn't change it at all. So what can we say about this matrix that I've called question mark? Well, there should be one thing right away that's obvious. What can we say about the dimension of question mark? has to be the same as matrix A, right? If it's not, we can't do any addition at all. So like that at minimum we know. Now let's think about, so now we know what the shape of this matrix is going to look like. It's just going to have to look like the same shape as whatever A was. What about the entries inside of that matrix? What do those entries have to be? What was that? The same as A? So you're saying that if I had the matrix 2, 1, 1, and I add it to the exact same thing, I get the exact same thing back again? No, that doesn't work. Okay? What would these... Well, yeah! They would all have to be zeros, right? No. That's a different thing, but... Okay, so we can say that this question mark is a matrix where each entry is 0. We can also refer to this additive identity as the zero matrix. A little bit of notation here on the side. We're going to use the letter O to represent the additive identity. So if I have a matrix A plus that matrix O, I should get that matrix A back again. Why do you suppose we picked O? Because it looks like a 0. So we wanted to make it really intuitive for us. Okay? And just as a little piece of notation, so here we haven't specified the dimension of matrix A or matrix O. If they're not the same dimension, this isn't true. So often what we'll do is we'll include the dimension as like a subscript on these letters to indicate to the reader that we're just adding two things with the same dimension. So we'll do that. No, like we did it right now. But when it matters, when it's not clear that the dimensions have to be matching or whatever, we can do that to just add a little bit of specificity to something like that. Okay. So my next question I'm asking, what are the additive inverses for matrix addition? What do those look like? When we say additive inverse, what we really mean is, what can I add to matrix A to get back the zero matrix, or the additive identity? So just like before, right away, what can we say about the shape of A and question mark? They have to be the same. They have to have the same dimension, or else we couldn't add them together, and this problem wouldn't even make any sense. So if I wanted to be a bit more specific here, I would add in those subscripts to indicate the dimension, to show that everybody that, like, yeah, we're just adding things with the same dimension together. Okay, that's fine. What would the entries have to look like inside a question mark in order for this to work? Exactly. So they'd have to be the opposite or the negation of the corresponding entry in matrix A. Yes, all the entries in question mark are the opposite of the corresponding entry in matrix A. So a little bit of notation here. Guess what symbol we're going to use to represent these additive inverses? What do we think? How would I write the additive inverse of matrix A? What? Yeah, we'll write it as negative A. Okay with that? Worth pointing out that negative A would imply scalar multiplication of negative 1 to that matrix A, which would be negating every entry inside of A, right? Everybody feel so far so good? We haven't done anything super tricky. We're just kind of spelling out like properties and whatnots. Getting used to thinking about like matrix addition, scalar multiplication. The next thing we should talk about is the question, is matrix addition associative? When we say associative, what do we mean? Well, we mean this, that if we're adding three things together, do I get the same answers if I add them in these orders? What do we think is going to be the result here? Is this going to be true? It sure is. It is absolutely true. And the reason why this is true is because guess what the real numbers are? They're also associative. So we would do this the same way we would do showing that the two matrices are commutative. We could do it in the exact same way. We won't do that here because it's a lot of writing because there's three matrices involved and it's just kind of a pain. But it would work. The explanation would work exactly the same way. And once you've seen it once, we probably don't need to do it again. It's the same trick, though. Okay. Let's start talking about scalar multiplication. Is scalar multiplication commutative? So what does that mean? Is k times a the same as a times k? Remember that k is a scalar, though, right? And it's just a real number, not a matrix. Is this true? Jack says yes already. Why is that going to be true? Because when we do the scalar multiplication, it just turns into multiplying each entry by real numbers, and two real numbers multiplied together is commutative. So this is absolutely yes. Good. We'll ask then, what is the multiplicative identity for scalar multiplication? When we talk about a multiplicative identity, what are we talking about? Something where I do k times a and I just get a back. This should be obvious, right? What does k have to be? Okay, but which specific real number? 1, right? I think that's us. So we'll continue this discussion on Monday. Yeah, on Monday. You guys don't need to do anything over the weekend. Catch up on